Hi everyone, this is video 7, and today we're going to talk about an even more powerful tool for abstraction, higher order functions. Before we talk about higher order functions, let's talk a little bit about generalizations and how this applies to defining functions. Whenever we define functions, it's important that we be as general as possible. And a good example of this is the built-in power function in Python. So, for example, you might have noticed that I've been defining a lot of square functions and cube functions, and you might have wondered, hey, why is it that these functions are not built into Python? Well, the reason they're not built in is because they're really more specific cases of the power function. You can square things by using the power function, you can cube things by using the power function, so there's really no reason to have a separate cube function or a square function to do something that the power function already handles. And this is an example of why generalization is really good, because general functions can do a lot of different things. But let's talk about a specific example of that. So to do this, I'm going to look back at an old friend of ours, sum naturals, which we defined in the last video. And remember, this computes 1 plus 2 plus 3 all the way up to n, and this was our definition of it. Now, what if we wanted to define the sum of squares? Okay, so this is an interesting problem, but after some thought, you'll realize that really it's the exact same definition as this, except instead of adding just an I, we're going to add an I times an I. And that's all it takes to get this definition for sum of squares. And then, what if I asked you, hey, can you define a sum of cubes? And then you might think again, well, isn't it really just the same thing? It exactly is, except now we do I times I times I. Now, I just broke one of the biggest rules of programming, in that if I'm copying and pasting code, there's a chance I can get an abstraction here. So I don't really need 30 lines of code to do all this. Really, I can do this with one function. And this is going to be our first example of a higher order function. So let's take a look at this. Let's say I want to define a general summation function that sums up anything with any type of term. So in our case, we want to handle just summing the natural numbers, summing the squares, and summing cubes naturally. So one thing we notice is that at the end of the day, the summation function is just some result, and then we do it plus some term that's a function of I. So this is why we have an abstraction waiting, because if you look at all of this, it's the same code except this last term right here. So what we can do is we can actually make this a function, and what we have is we can put term as one of our parameters, and we can just call every single time, we can call term of I. And what this term is going to be, it's going to be bound to particular functions that define what we're summing over. Summing. Okay, so now this might be all very abstract, so now let's look at some examples. So I also defined these 3 functions just to show you in this example. So I'm going to run this interactively, and I'm not running tests on this because this is relatively simple. I'm quite sure they work, so that's all. And we already tested the sum naturals, so these are bound to work. So let's look at our sum naturals of 10. That should give us 55. We also can do the sum of squares of 10 and get that. We can also do the sum of the cube, and we get that. Okay, so now those were 3 specific functions I did to do 3 different things. But now I have a general function that can do all of this. Now watch this. I'm going to call summation of 10, and then to do the sum naturals, I want it such that this term of I just returns I. Do I have a function that takes in an I and returns an I? That's my identity function. So I pass it in with the identity, and I get exactly the same thing as the sum naturals. And then if I pass it in with the squares, the square function, I'll get the exact same thing. So this is pretty cool because we can pass in functions as our arguments, and we can do operations with that. So this is an example of a generalization. So in reality, I don't even need these functions. I didn't need to write any of this code. I didn't need to write any of this code. So I can just erase that, and then now I have a function that's only 7 lines instead of more than 30 lines that represents the same thing that those 3 functions could do. So this is why generalization is so powerful, because we can now take big ideas and express them very succinctly. So now we've seen our first definition of a higher order function. And a higher order function, formally defined, is a function that takes in a function as an argument or a function that returns a function as a return value. We haven't seen the second case yet, but I'll show you an example of that. So here's our summation function, and with these 3 helper functions that are very simple, we can do several operations. And the cool thing is that we can define another function now that takes the power to the 4th power of a number, and we can sum over that too. So this is a very powerful way to show generalization, and higher order functions are great because of this. Now, let's look at a function that returns another function as a return value. So let's say I want to make a specific adder that adds numbers to other numbers. So I'm going to take in a number, and what I want this make adder to do, I want to make a function that adds 3 things. Okay, so let me just do doc tests on this. So if I want a function that adds 3 to things, I'll just make an adder of 3. And now I should have a function that adds 3 to things. To 5 should give me 8. Add 3 to 10 should give me 13. And so yeah, that's how this function works. And how do I do that? Well, at the end of the day, I know I need to return a function. So inside this, what I can do is I can return that function I want to return. I can define the function that I want to return. So if I define an adder that takes in a number k, and what I want this adder to do is I just want it to simply add the n to the k. And then at the end, what I can do is I can return the adder. So what this is going to do is let's just test it, see if it works. So I'm going to do Python doc test this time. Python-m doc test video 7.py, and it works. But now also to look at some more examples of how this works. Python-i video 7.py, and let's say I want to make a number that adds 5 to things now. A function that adds 5 to things. Well, I can just make an adder now of 5. And this is very useful because now I have a function that adds 5 to numbers. So I can make any type of adding. I can make a number that adds 24. I can make a number that adds several different numbers. And I can make these all on the fly by just calling this function. So this is why a function that returns a function is quite useful. Now, I can also do something like this. I can make an adder of 6. So now this is something that adds 6 to things, and I can add it with like 13 or something, get 19. So this is two examples of how we can use this function. But overall, so this is pretty useful. Now let's look at a little bit deeper into the execution of such a function. So here's our function as return values example. So here's some more examples of that. And again, nested def statements are required to return a function within it. And lastly, let's look at this expression tree. So the expression tree for this is a little different than usual in that we have a call expression here. And this call expression actually ends up returning a function, which is the adder function. And then we call it on 4. And then what does this do? It returns n plus k. What was the original n we had? It was 3, so that's 3. And then what's our k? It's 4. So we just return 3 plus 4 and we get 7. So that's how this works. So the expression tree still works, but it's just a little different in that one of our return values is going to be a function. Now, the next function I want to talk about is a special type of function called the lambda function. And this is very, very useful for defining functions on the fly. So, how do we do this? Well, what we can do is, let me just show you examples of how this works. So, let me make sure you can see the syntax for this. So, I'll favor function square to differentiate from a normal square, I'm going to call it square L. And what this is going to do, I can define a lambda function for this by doing lambda, a keyword. What's the formal parameters of the square? It's x, and return x times x. So that's our first lambda function, and now I have something that can square things. So it works just like normal functions. There's a few things that are a little different, but we'll talk about that in the next video where we talk about environments. Now, what we can also do cubing of functions. So for example, if you want to directly call your function, lambda function, what you can do is put parentheses around it. Let's say I want to cube a number. I can cube 5 and I should get 125. So that's how lambda functions work. Now, something interesting, you can also do higher order functions with lambda functions. So if I want to use my make adder with the lambda, what I can do is I want to have a lambda function. So, oh, by the way we read lambda functions is we say this is a function that takes in x and returns x times x. This lambda function is a function that takes in x and returns x times x times x. So now, with this make adder, I want a function that takes in an n and returns another function that another function that takes in k and returns n plus k. So this is my make adder function, and so let's say I want to make an add 7 function. I can just call make adder of L on 7, and sorry, what did I do? Oh, I need make adder. And then once I have this, I can just call add 7 on numbers. So if I do add 7 on 8, I should get 15. So that's how lambda functions work. So, what have we talked about so far? We've talked about lambda functions, we've talked about higher order functions. And what I wanted to show in this video is just a broad overview of these different types of things, a little bit of new syntax and how this works. In the next video, I'm going to go over how this works with the environment diagrams, and then we'll get a deeper understanding for exactly how higher order functions work. Today, I just want to kind of expose you to how all of this works.